Hello everyone, welcome to my video about math proofs. This is just gonna be a beginner's video to math proofs. They're gonna be pretty simple, pretty easy proofs to do, and they're just gonna help you get a understanding in case you don't have one of math proofs. So hope you enjoy. So proof one, we're gonna try and prove that n is always equal to the square root of n squared, given that n is some natural number. For this proof, of course, we're going to use induction because that will be the easiest for us. And so we have two cases here. Case one, if you believe 0 is a natural number, it's a commonly debated thing in math. Then we're going to set the base case as n equals 0, in which case we have proved that the base case is true because 0 does in fact equal 0. Then we are going to assume that n is equal to k. That statement right there is true, we're assuming. And then we're going to show that n equals k plus 1 is true. If you look down here, k plus 1 equals k plus 1. That means that this is true, because when you do the algebra, it equals a true statement. So that's case 1 is obviously true, always. Case 2 is if you believe 0 is not a natural number, in which case the base case is going to be n equals 1, because that's the first natural number after 0. And you get 1 equals 1 when you do the algebra, which is true, which means that the base case is true, which means we can now show, assuming that n equals k is true, we can show that n equals k plus 1 is true. And if you, once again, do the algebra, you square both sides, get rid of that square root both sides, get rid of that squared, and then subtract 1 from each side, you get k equals k, which is true, meaning that since the proposition is true for a base case and for every subsequent value of n, in both cases, it is a true proposition. Okay, next up, we got proof 2, and this proof is basically asking that to prove that n squared minus 4n plus 4 equals 9 for any and all numbers n in the set of 5. So to do this, of course, we're going to use contradiction, as it will be the easiest for our stuff. So first we're going to assume the opposite of the proposition. So we're going to assume that there exists a number n in set 5 such that n squared minus 4n plus 4 does not equal 9. With this, we can factor it out into a n minus 2 squared, and then do some algebra to get that n minus 2 does not equal plus or minus 3 in this assumed contradiction. And then if you do some more algebra, you can see that n does not equal 5 if n is in the set 5. And since case 1, we have n equals 5. 5 does not equal 5. That is a contradiction, meaning that that would not work. And since that is the only case possible, since the set only has 5 in it, we have that the proposition is true, because if assumed the opposite, we run into a contradiction, meaning that n squared minus 4n plus 4 equals 9 for any and all number n in set 5. Proof 3, we got prove that k is even, or prove that if k is even, the number k is going to be even. Now for this one, it doesn't take a genius to figure this out. We're of course going to do proof by contraposition, whatever. It's kind of hard to see, so I'm just going to highlight it for you. If the proposition is true, that if k is even, the number k is even, it follows that the contrapositive, if the number k is odd, k is also odd, is also true. So we're going to assume, or we're going to replace k with the definition of an odd number, which is 2n plus 1, where n is some integer. So k would be equal to 2n plus 1. So when you sub that in, you get 2n plus 1 equals 2n plus 1. 2n equals 2n. divide each side by 2, you get n equals n. And since the contrapositive is true, that means the proposition also has to be true. Due to like De Morgan's law or whatever. That's not okay. Proof 4. We're gonna have a proof that says that n plus 1 is always greater than n, given for any and all n in real numbers. So for this proof, obviously we're going to use a direct proof because that is the obvious choice here, and it's the most reasonable to use for this one. So for this proof, we're going to, of course, need a few cases. So first case is if n is less than -1, we got to flip the sign of the inequality when doing some sorts of operations. So since if n is less than -1, both sides are negative. When squaring it, you have to flip the sign. So we have n plus 1 squared is actually less than n squared when n is less than -1. And of course, we can integrate both sides from 3 to 8, or -8 to -3 because it's the same thing. And that is, of course, going to get us to our answer. But we also have to flip the sign again since n is still less than -1. Both sides are negative, so we got to flip the sign again. And then once you evaluate those integrals, you get 221.6 repeating is greater than 161.6 repeating, which is obviously true because that's how numbers work and whatnot. And that brings us to our second case. So case 1 is proven. Our second case is if n is in between -1 and 0. Now, if this is true, we're going to do a pretty complicated process, and that is just subtracting 1n from each side. And that will get us 1 is greater than 0, which is obviously true because that's, once again, I think how numbers work, if I read it right. So, if I know correctly. So that brings us to our case 3. Now that case 2 is proven, case 3 is that if n is greater than 0, what we're going to do here, obviously, is we're going to square both sides, but this time we won't flip the sign since both sides are positive, so we don't have to do that. Then we're going to square both sides again. Set e to the power of it, so we can get it in a form that's better. Then we're gonna, of course, convert it to a Taylor series. So z equals 0 to infinity, the sum of from 0 to infinity of n plus 1 to the 4th to the z over z factorial, since that's the Maclaurin series for e to the x. And we do the same for the other side, n to the 4th to the z over z factorial. Then we're going to add 1 to both sides, and then, of course, we're going to take the natural log of both sides. Now, we're getting pretty close to an answer here, but the last step, I believe, is going to be taking another Taylor series for ln of that plus 1. So, of course, we're going to have from k equals 1 to infinity, -1 to the k plus 1 of the series from 0 to infinity of n plus 1 to the 4th to the z over z factorial over k is greater than the infinite series from 1 to infinity of -1 to the k plus 1 times the infinite series from 0 to infinity of n to the 4th to the z over z factorial to the k over k. And so this is the series for natural log plus 1. So this is still true, it looks like. But yeah, here it's obvious that there's actually no way of solving this proof. So this proof is completely undecided from all fields of math. No one knows how to solve it yet. So we have no idea if this proof is true or not. It's completely unprovable. So I don't really know what to do from here. But if you guys want to take a crack at it, you might get like a Nobel Prize or something. That's still not okay. So for proof 5. You need to prove that the sum of all interior angles of a square is equal to 360 degrees. Now, this proof is actually minorly complex. It might test your skills a little bit, but for the most part, it's still pretty simple. So, of course, we're going to do a direct proof for this one because I don't know what you expected. So first, we're going to assume a square S of sine length L that touches the y-axis of a graph. And then we're going to rotate it about the y-axis to form a solid. And that solid is going to be an oblate spheroid whose volume can be assumed to be approximately the double integral from a to L and B to L of L cubed times e to the infinite series from 0 to infinity of the kth root of 3 theta k minus ln k times the infinite series from 0 to infinity of -1 to the nth theta 2n plus 1 over 2n plus 1 factorial dl d theta, where theta is, of course, the interior angle, and a and b are the lengths of the chords leading from each vertex of the cross-sectional ellipse to the nearest point on that ellipse, that of the cross-sectional angle of the solid. Because of the interior angle actuation theorem, we can assume that the interior angle of the solid is equal to the sum of the interior angles of the square that we used to form it. So when the proposed integral is solved, it can be found that the interior angle is not, in fact, the sum of the angles of a square with any side length, which is actually 360 degrees, but it equals some random value instead. Therefore, the sum of a square's interior angle is 360 degrees. Now moving... Okay, moving on to our sixth and final proof. We're going to prove that if given a collection of sets which are non-empty, it is possible to construct a new set through choosing an individual element from each set. Now, this one is very interesting because it's probably the most difficult one we've done so far in this video. So if you want to pause and try and solve it yourself, feel free to. But if you can't, it really is a really advanced one, so it makes a lot of sense. So to solve this, what you're going to want to do is first realize that this is the axiom of choice, and that since it's an axiom, it's assumed to be true, because axioms are assumed to be true, and so we can assume that this is true. Next up, is our final proof. So what we can do here is no, not that. Thank you, and then to conclude, it's just thank you. And if you liked the new video, make sure to subscribe. Subscribe, and then tell me what I need to do. And tell me, don't tell me if I made mistakes. I don't want to know. Hope you guys have a great day. See ya.